someone reported some progress. And yeah, we have a talk by Daniel Kroll in the afternoon. So our first speaker this morning is Laszló Miklos Lóvasz. He'll be talking about arithmetic removal lemmas for triangles and k-cycles.
Thank you for organizing this workshop and for inviting me to give a talk. It's my first time in Rio, and it's been great. So this is joint work with my former advisor, Jacob Fox, and his student, Lisa Sauerman. So I'll give an overview of arithmetic removal lemmas, and then talk about our upper bound, say a few words about our upper bound proof for triangles, say even fewer words about our upper bound proof for k-cycles, say something about lower bounds, and then discuss what's still open. Okay, so let's start with graphs. So a well-known theorem or lemma in graph theory says the following. So basically what it says is if you fix a graph H, and in a dense graph you have few copies of H, then you can remove a small number of edges, a small fraction of the total possible number of edges, to make the graph H-free. So you could have on the order of n to the number of vertices of H, copies of H. So here we're saying that it's much smaller. And then the way you do the quantifiers is for any epsilon, there exists a delta, so that if you have less than delta fraction, then you can remove less than epsilon fraction of the edges to make it H-free. And this was proved by Ruja and Semeredi for triangles, and then Alon, Duke, Lefman, Riddle, Yuster for graphs. And the proof involves using the regularity method, so the regularity lemma, and then counting lemma. And this is a very important use of the regularity method, and it has many important applications in extremal graph theory, in additive number theory, in theoretical computer science, and discrete geometry. And maybe just to mention, so we know that if this is small, then this is small, but how small? So the bounds that you get are actually very weak. So the way I like to think of it is you're thinking of how big does 1 over delta have to be in terms of 1 over epsilon. And the bound that you get is tower type. So I'll go more into this later, but it's a tower type function of some power of 1 over epsilon. To see when this came out, that was the bound that was obtained. So this is a huge bound. Now, one implication of the triangle removal lemma is Roth's theorem. So you can use it to prove Roth's theorem, which says that if you have a subset of the numbers from 1 to n, and there's no 3-term arithmetic progression in this set, then the size of this, the maximum possible size of this set is sublinear. So the maximum possible density goes to 0. Now, since we saw there are tower type bounds, so that you can perhaps guess that that proof would give terrible bounds for this. Roth's proof gives a bound that's of the form n over log n, so very slowly, but better than what you get from the tower type. And I believe the best known bounds are of the form n divided by log n times some other lower order terms due to Sanders and Bloom. Now, from the other direction, a construction of Barron gives a lower bound that is of the form n over e to the c root log n. So it's a huge gap. So this shows that it's not n to the 1 minus epsilon for any epsilon, but it's not much bigger than that. And the reason I wanted to mention this, one reason I wanted to mention this is actually the best type of bound we have for the graph removal lemma. So since the triangle removal lemma implies Roth's theorem, a construction for Roth's theorem gives a construction for the triangle removal lemma. And so this implies a lower bound on 1 over delta that's super polynomial, but just barely. So there's a huge gap here, So what we're going to do now is, if we can't solve a problem, go to another setting for a related problem, or solve the problem for a special class of graphs. So let's move to the arithmetic setting. So now so in this talk, we're going to be working in fp to the n. You can work in abelian groups, but here let's stick to fp to the n. So a k-tuple, we'll say that a k-tuple of numbers in fp to the n forms a k-cycle if they sum up to 0. And then Green proved an arithmetic k-cycle removal lemma, which says basically the same idea. If you have a small number of k-cycles, then you can remove a small number of elements to get rid of all k-cycles. And the precise formulation, so here you could have n to the k minus 1 different k-cycles total. So by small, we mean less than delta n to the k minus 1 for some delta. And then by removing a small number of elements, we mean less than epsilon to the n, where here big N is the total number of points in fp to the n. OK. So Green proved this for general finite abelian groups. And he proved it by developing a regularity lemma in the arithmetic setting based on analyzing Fourier coefficients of sets, which in fp to the n is just distribution on hyperspace, affine hyperspaces. Now, Kral, Serra, and Vena gave a proof of this, which holds actually for general groups using, and they showed that it follows from the graph removal lemma, the directed version, but you can also prove it for directed graphs. So, which means you can kind of think of this as a removal, as looking at a special class of graphs. Let me briefly indicate their proof. So what they do is, if we have 3 sets in fp to the n, we want to show that if there's a small number of triangles between these 3 sets, then we can remove a small number of elements to get rid of all triangles. And so they define an auxiliary graph G, and they show that applying the graph removal lemma to this G implies the arithmetic removal lemma. And the construction of G is pretty simple. You take 3 sets, each of which we're thinking of the 3 sets of vertices, each of which correspond to fp to the n. And now the way we take edges, so between the first 2, we connect u and v if u minus v is in x. Between the second 2, we connect v and w if v minus w is in y. And between the third pair, we connect 2 points if w minus u is in z. And then you can check that triangles in x cross y cross z correspond to triangles in this graph. And then if you apply it with a little work, you can obtain the arithmetic removal lemma. So what do we have now in terms of bounds? So let's go into this more precisely. So here's the precise definition of the tower function. And then Green's proof of his removal lemma also gives this tower type bound. So 1 over delta is at most a tower of height 1 over epsilon to the c. And well, since when the Kral-Serra-Vena proof came out, those were the types of bounds we had for graphs as well. So the Kral-Serra-Vena proof would get you the same type of bound. So Green asked, can you improve the bounds in the arithmetic removal lemma? So a theorem due to Jacob Fox from about 2011, I think, is that in the graph removal lemma, so he proves that you can take, so he proves an upper bound, which is still a tower function, but the height of the tower is logarithmic in 1 over epsilon. So obviously it's bigger than any exponential, double, triple, any such exponential, but it's also smaller than any polynomial tower height. And so you can get the same bound for the arithmetic k-cycle removal lemma. So for any k, you have 1 over delta is at most tower of height log 1 over epsilon. Now, in terms of lower bounds, this was studied in f2 to the n, and Bhattacharya and Shi gave a lower bound on 1 over delta, which is 1 over epsilon to some power. And then Fu and Kleinberg improved this exponent, so they gave a lower bound in f2 to the n for triangles of the form 1 over epsilon to the roughly 13.239. But until recently, nothing better was known for fp to the n. So now it looks like the situation here is even worse, because now we don't even have a superpolynomial lower bound. We just have a polynomial lower bound, and then for an upper bound, we have this tower-type function. So our result is that for every prime p, we can take this 1 over delta to be a polynomial in 1 over epsilon in fp to the n. So for p equals 2, the bound that we get is this number 13.239, which is the same number that I had on the previous slide. So this matches the lower bound due to Fu and Kleinberg. And for p at least 3, we also obtain a lower bound it has an explicit formula, which is tight by a result of Kleinberg, Solomon, and Spire that I'll mention in a second. Sorry? Kleinberg, Solomon, Spire? Yes. Yeah. Well, yeah. So it's Kleinberg, Solomon, and Spire. Yeah. Yes. Well, they can also get a type bound in some sense, and then, yeah.
If you have just memory, it's enough.
Okay. Yeah, so I probably should say that there's, yeah. So they have a conjecture, and then Peabody proved that conjecture, and then that shows that it's tight. And now for general K, so here we thought, okay, we proved it for triangles, but the proof should go through for K cycles, because why wouldn't it? But it's actually not, this proof doesn't, at least we didn't see how to make it go through for K cycles. With Lisa as well, we have been able to prove a polynomial upper bound. So there exists an explicit CPK. But for this problem, we don't have a type bound. But we have obtained a polynomial bound for it. OK, so let me say a few words about the upper bound proofs. So let's start with triangles. So we use the recent breakthrough results on cap sets and 3 APs. So let me summarize those. So here, the question now you can analyze this for a general abelian group. How large a set can you have without a 3-term arithmetic progression? And in the case of f3 to the n, this received particular attention. It was called cap sets. It's also related to the game of set, if you know the game. And Meshulam proved, in this case, an upper bound on the size of x of the form 3 to the n over n. And this was improved by Bateman and Katz to 3 to the n divided by n to some larger than 1 power. Now, on the other hand, in terms of lower bounds, how large can it be? Well, it's not hard to construct a set of size 2 to the n. And Adel has a construction that's of the form 2 to the roughly 2n74 to the n. So up until recently, this was yet another one of these problems where there's a huge gap in our understanding. So a breakthrough result due to Kroot, Lev, and Pach was in Z4 to the n. If a set has no 3-term arithmetic progression, then the maximal possible size of this set is 4 to the Cn, where C is an explicit number less than 1. So this is a completely different type of bound as here, where you're just dividing by some polynomial in n. And then soon afterwards, this was extended by Ellenberg and Heisweit to, or their method was used by Ellenberg and Heisweit to show that in fp to the n, if you have a set which has no three-term arithmetic progression, then the maximal possible size of this set is at most p to some power strictly less than 1 to the n. So it's an exponential improvement again. And so in this paper by Blasiak, Church, Cohn, Grachow, Naslund, Sohn, Umans, and independently Alon, they observed that the same bound actually holds for a more general problem, the multicolored sum-free problem. So here you don't have one set, you have three different sets, x, y, and z, which are each ordered from 1 to m, and you have the property that xi plus yi plus zi sums to 0, but no other triple sums to 0. So this is called the multicolored sum-free problem, and the reason it's an extension is because you can take x and y to be a, and z to be minus 2a, and then if a is 3ap free, then these three sets form a multicolored sum-free set. And this proof actually shows the same bound for the multicolored sum-free problem. And then this is sharp. So for F2 by construction of Fu and Kleinberg, and then for FP by Kleinberg, So, and Speyer, and then a conjecture proved by Peabody, it's sharp.
So can I ask a question?
Yeah.
By sharp you mean the exponent?
Yes, sorry. Yeah, so what I mean is that A is at least this minus little o n. And we use this as, so this result we use as a black box. So I'm just going to need this result. No. OK. So here's our theorem. So what we prove, so first we have this slight reformulation of our theorem, which is that if you have three sets in fp to the n, and you have epsilon times n disjoint triangles, then there are at least epsilon to the power to the c n squared triangles in their cross product total. So the reason this is basically a reformulation of the theorem is up to a constant factor is that if the number of points you need to remove to get rid of all triangles and the number of disjoint triangles you can take is within a factor of 3 of each other. So this goal suffices for our purposes. And in fact, I claim that actually it suffices to prove this with a little o1 in the exponent here. So here this little o1 is as epsilon goes to 0. And the reason for that is because if you have a construction, you can take a product construction and you can use that to kind of get rid of the little o1. So a kind of product trick lets you get rid of it. OK, so let me just sketch our proof. Let me stick to the F2 case. And should mention that what I'm sketching now was simplified by Lisa Sauerman. It was a bit more complicated the first time. But so let me just talk about our main lemma. So first, assume we have these three sets x, y, and z. Suppose they're disjoint, and suppose that each point in any of them is in at most some lower order terms times delta over epsilon times n triangles. So on average, the points will be in delta over epsilon times n triangles if there are delta n squared triangles total and epsilon n points. So it's perhaps not a crazy assumption to assume that this holds. And then we take a random subspace, W, whose dimension we've chosen to work for us. And then we take the intersection of each of these three sets with W. And now, so we call the triangle in this product good if it's the unique triangle for each point. So if x prime is not contained in any other triangle, y prime is not contained in any other triangle, and so on. And now the claim is that because of how we've chosen this dimension of W, the...
You mean inside x prime, y prime, z prime?
Yes. Yes, so we take...
Triangle within x prime, y prime, z.
Yes, 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 thanks. And now what we claim is that if we have a triangle in x cross y cross z, if we condition on this triangle being in our subspace W, then it's good with the probability at least a constant, which for us is 2/5. And the basic reason is that the size of this set has been chosen so that basically the 1/2 to the d roughly cancels out how many points an element is in. And if you fix x, say it's contained in a bunch of triangles, and once x is in the set, it's roughly independent whether the rest of the triangle is in the set, and you only need one more event to happen, is in the subspace. So that's the basic idea of why this works. And then once we have this, we can take a subspace of dimensions d with roughly the same density of good triangles. And then the definition of good triangle means that they form a multicolored sum-free set. That's basically the definition of multicolored sum-free. So what we show is that epsilon and delta roughly stay the same, and then to this set we can apply the multicolored sum-free bound, and it translates into the bound on epsilon and delta that we need. And then in the general case, we delete points that are in too many triangles, make sets disjoint, and if we do this carefully, then epsilon and delta don't change by too much. Okay. Now let's first see why this doesn't work for k-cycles. And then let me mention what we did do for k-cycles. So here's our theorem. So the first step is the same. We say that we can take epsilon and disjoint k-cycles and just argue that that implies that there are a lot of k-cycles. We can do little o1 as before. Now the multicolored sum-free result extends to k. I'll say more about that later. So what we used in the triangle proof is that if we have two different triangles that intersect in their first point, then once x1 is contained in W, the events that these two triangles are both contained in W are roughly independent. The dependence is lower order. And this allows us to make this proof work, that with a positive probability, we end up with just one of them in the set. And this is easy to see in F2, and you can add some dummy coordinates to make it work in FP. But this is very much false for larger k. So if we have these two k tuples, they can intersect in multiple ways. They might intersect in 1 point, 2 points, 3 points, and so on. Furthermore, there's another thing that can go wrong, which is for example, they might intersect only in x1, but then you might have another linear relation between the x2s and the x2 primes, and that affects the joint probability. And so that makes it much more complicated. So the best bounds that we've actually been able to obtain are just by induction on k, using k equals 3 as kind of a black box base case. And so the bound that this gives is basically once you subtract 1, it scales linearly with k. I don't want to go into this induction argument because we don't have time, but basically you can find a subset of the coordinates and then contract them into 1 point and apply induction there. Okay, now what do we have in terms of lower bounds? So let's make this k multicolored sum-free set definition precise. So it's basically the same thing as for triangles, but here's a precise definition. And it's kind of folklore based on the formulation of the proof that appeared on Terry Tao's blog that it extends to k to give a bound, on the maximal size of a k multicolored sum-free set. So this construction actually hits similar challenges when generalizing to k bigger than 3. The construction starts with the set of triples and then samples a random subset and actually uses some similar arguments to then take the good ones and use that to form a multicolored sum-free set. And because k cycles can intersect in much more complicated ways than triangles, it's more complicated. Now here we have managed to make it work with some additional ideas. So we have been able to come up with a lower bound construction with Lisa for the k multicolored sum-free problem, which is sharp, which matches the upper bound in the multicolored sum-free problem. And this, so a construction for the multicolored sum-free problem gives a construction for the removal lemma. Basically, the removal lemma implies the multicolored sum-free problem relatively easily, and so a construction for it gives a construction. So now if we look at the bounds, so our upper bound is basically this expression here from the induction argument. And the lower bound implies a lower bound on CPK, and if you go through the algebra, what you get is here. So I find this kind of interesting that it's almost the same expression, except here you have CP3 and here you have CPK. So it's kind of like because we're forced to use induction, the only bound we get on from the multicolored sum-free is what we get on the triangle case, and so that's the best. If you could somehow figure out a way to combine various constructions of the multicolored triangle sum-free problem, perhaps you could match this, but this is the best bound that we've been able to obtain. Okay, so some further questions. Well, it would be interesting to close this gap. Maybe I should mention that I think this grows on here. There's kind of so this grows linearly in k, and here, well, this grows, there is a linear k plus log, I think this grows like k plus log k, whereas this grows as some larger constant times k. So the gap is kind of, once you subtract k, it's log k versus k. Another extension of this question is, so we've now bounded the size of a 3AP free set. Can you bound the size of a 4AP free set or no a k-term arithmetic progression, or a set without any k-term arithmetic progressions? And if you can you get a removal lemma with good bounds? More generally, you can just ask if you have k sets and multiple equations, you can prove a removal lemma, but can you get one with good bounds? Finally, can any of these techniques help with the graph removal lemma? One thing that we can say about this is in the triangle case for graphs, there's also the diamond-free lemma, which kind of corresponds to the multicolored sum-free problem. And we can show that if you can prove the diamond-free lemma with good bounds, then you can do a random sampling argument and get a removal lemma with good bounds. So maybe that's the way to proceed, but this still seems to be very difficult. And thank you for your attention.
Questions?
In the first question, the two sides are about what?
So